Welcome everybody. Most exciting day of the year. It's the start of the new school year. Hey, you're not as excited as the professors. We're not excited either, but we're going to get excited. So, welcome to Quantum Optics 2. We will, as has been the habit for a number of years now, be videotaping the courses. We're going to try to get them, though, onto YouTube, our new YouTube channel for CQuick. So that's going to be one of our experiments. So the TA for the course will be Izad Shojehi, if you don't know Izad. We will be talking then about the plans, the administrative plans for the course, just to get started. So let's see. Firstly, this is an advanced topics graduate course. So the purpose here isn't really to quiz you deeply and to make it a giant hurdle. But to give you the tools you need to pursue the research you're doing. Or if you're generally interested, that's great too, even if you're not doing research in this area. But there will be no exams this semester. There will be, though, a final project, which will be somewhat substantial. And let's see, where is all of that information? So here it is. So, bigger here. So the course will be based on homework and the final project. The homework will be assigned about every other week. There'll be longish assignments that have, because there's a lot of work to be done to mass this material, involving some serious analysis, and it takes some time. So there'll be homework about every other week, and then there'll be, at some point, we'll stop doing that, and you'll be on the track to do your final projects this semester. So we won't have a formal problem session for the course, but I will have office hours. Izad will have office hours, and so we will send around a little poll for trying to arrange those times for you. All right. As you know, this is Quantum Optics 2. There was taught last year Quantum Optics 1, and I know a number of you here were not there. So, how's it going to go? Well, a certain amount, we will do a certain amount of reviewing here of some of that material, but not a heck of a lot. Some amount of the things that we worked on last year, we will draw on in this semester, and it will be important. And so I'll emphasize where those things are as we go, and if that is material that you need some extra help with, let me know. And we have time in other parts of our discussion to have some review sessions on some of that material if you need a brush up. We did a little bit of that this summer for those of you who were around, but it would make room for more. Okay? But I'll work with you on trying to fill in those holes where they need to be filled in. Let's see, what else? There is no textbook for this course yet. But I'm going to be taking sabbatical next semester, I hope. I need to apply for that. With the goal of trying to really make some progress on the book. So I could use your help, which means if you go through the notes, you see mistakes. I would never dearly make one, but occasionally my friend does get out my notes and mess with them. So I would appreciate you pointing them out and things where you think the notes can use improvement, because this is going to be the basis of the book. All right. Anyone who's good at LaTeX, I wouldn't complain. But anyway. All right. What else can I say? So let's talk a little bit about the subject matter of this course. Here's the sort of tentative syllabus here. Where we're going to talk about, there are sort of a few, I would say, main topics that we're going to cover this semester. Part of it, the first topic is really something that could have fit in more contiguously with what we discussed last semester, which was some discussion about what we mean by classical light versus non-classical light. Something that was the topic of last year's course in Quantum Optics 1, but there was sort of a missing topic that we never really got to, which had to do with the question of squeeze states and their relation to classical versus non-classical light. But this will give us a kind of transition into the problem of entanglement in quantum optics. That would be our launching point, which would be a main topic of this semester. And in particular, that will connect us to the problem of open quantum systems and measurement and decoherence, which is really going to be the main topic of the semester. Okay? And so we're going to dive deep into that. If we have some time, depending on how fast we go, we might get into some of the particular applications, modern applications of quantum optics in quantum information science, in particular applications in quantum communications and computation metrology, but we may not get that far. We'll see where we get. All right, so that's the plan for the semester. As always, all the notes will be posted here, and the links to the videos for your watching pleasure. All right. So what we see here is we already have coming up on Thursday. I won't be here. I have travel, so we won't really get going until next week. This is the only travel I currently have on my schedule. I will be gone for lecture next Thursday, so we won't have class then. We'll make it up at some point. All right, but otherwise, there's no other travel on the schedule. All right, this, it's important you have the URL. It is linked on the department's list of classes, so you can find it there. Okay, anybody have any questions, concerns? Yes, sir.
Are you going to backdate previous lectures?
What's that?
For Quantum 1 into YouTube, something?
Yeah, ultimately, yeah.
But not yet?
We haven't done anything yet.
Okay.
But that's the plan. We plan to get that going this semester. I mean, you can still find the old URL still works and everything is still there. It hasn't been taken down. So, but ultimately, we do intend to move it onto our YouTube channel. Anything else? All right. Very good then. Well, let's get started. All right. So just to set the stage a little bit, remind ourselves what the whole subject matter is about and how it connects. We're talking about quantum optics. And I would say, quantum optics is really at the birth of quantum mechanics itself. If you think about it, the development of quantum optics was at the first dawn of quantum mechanics in the question of waves versus particles. So, going back even pre-quantum optics, of course, we can ask ourselves, what is the nature of light? Is light composed of, is light a wave, or is it composed of particles? And at the end of the 19th century, this problem was sort of settled. Waves win. And that was definitively shown by Young in, the famous Young's double slit experiment, Young's pinhole, and then you have this double pinhole and screen. And if we look at the intensity on the screen, it shows this interference pattern, interference between interfering waves that can land on the screen. And of course, Maxwell answered for us what the heck it was that was interfering. So the Young double slit experiment demonstrated the wave nature of light by showing that light beams interfere with one another. We understood interference as a property of waves. And Maxwell, of course, taught us that what interfered, that this was an electromagnetic wave. And that was that. But of course, that story didn't last for very long. In that, at the sort of dawn of the 20th century, here comes Planck and Einstein. Which kind of resurrects the corpuscular theory, as we like to want to say, the word corpuscular, of Newton and such, in the sense that there was a notion of the quantum of light. The photon. So this gives us, sort of resurrects the particle idea that in some sense light is composed of particles. And trying to reconcile these different pictures is in some sense how quantum mechanics was born. How was it explained? The fact that light is composed of photons, but nonetheless, we observe interference, is that what is interfering here is now, so Maxwell's told us what interferes in electromagnetic wave, but with the quantum theory, now we have interference of probability amplitudes. And those probability amplitudes, what are they telling us? So the probability amplitude, now psi, the probability amplitude, is something that tells us about the history of possible photon trajectories. So whereas in the classical theory we say, well, there could be some electric field that is coming from slit 1 and some electric field associated with the electromagnetic wave here, and the total electric field is the linear superposition of those electric fields, and thus the intensity, which is proportional to the square of the field, will exhibit interference between those waves. From the perspective of quantum mechanics, what we have are probability amplitudes associated with two possible histories of an individual photon, right? So an individual photon might move along this trajectory to reach the screen, or it might move along that trajectory to reach the screen. And if those two trajectories are in principle indistinguishable, so their history, so we see interference between indistinguishable histories that lead to the same final outcome. So the outcome that we're discussing here is now detecting a single photon at this point with some detector, and the probability that happened depends on the interference, of course, between those amplitudes. And if we look at then multiple cases, of course, we build up this interference pattern as a kind of histogram of that is telling us that some relationship between the frequency of occurrence of a certain event and the probability that that event occurs, right? And of course, because we have these two possible histories, we calculate the probability is related in the same way as the intensity, and this is of course why Max Born wrote down the Born rule, is because it was to try to explain what was going on in the interference of a double slit type experiment. That instead of intensity, we think about probability or probability densities in terms of which is the square of the amplitude, right? In this case, star psi, which will show interference between those possible trajectories. Okay? So, this kind of phenomenon, which shows an interference between two possible histories of a photon, it led Dirac's famous statement that single photon interferes with itself. There was some debate early on as to what was going on in seeing this interference experiment, as to whether what was really happening was there was some kind of interaction between photons within this beam versus the photons in that beam. And that's what led to this interference pattern. But Dirac sort of has a very stark statement in his book where he says, no. What is happening is an individual photon only interferes with itself. There's not interference between other photons with each other. Okay? So sort of photon by photon interference. And what interferes is this amplitude, this probability amplitude. The relationship between the probability amplitude for the detection of a photon in a certain place and time, and the electric field is one we'll come back to. In what way are they related? We see the analogy here, but what way are they really related to one another? Get rid of this before I trip over it. Now, of course, Dirac's statement was perhaps overstated, not incorrect, but must be taken in context, in the sense of an interference effect of this sort, which occurs photon by photon, which would be seen in a double slit type experiment, or in a Michelson interferometer, or a Mach-Zehnder interferometer, where there are two paths that an individual photon might take, and there is, say, two histories, or it could be multiple paths. It could be in the diffraction grating with many slits. It doesn't have to be just two paths. But anyway, these are photon by photon clicks. There's a single detector here. And there's only, say, in principle, I would see this pattern if I had a detector that, say, only counted one photon at a time. But there are other phenomena that we see that which in the early days of the development of the more modern subject of quantum optics led to great debate and great confusion. And this came a little bit later, but it's the most clear example of that, which is an example of the Hahn-O-Mendel two-photon interference. So here is an example of the following. Now I'm not going to have one detector, I'm going to have two. Okay? So I have a beam splitter, and I have two detectors, one at this output port, so this is my beam splitter. Let's say it's a 50-50 beam splitter, which means that half of the intensity would go one way and half would go the other, on either way. And I have two detectors here. So I have a detector D1 and a detector D2. Okay. And I can send light in simultaneously into these two input ports. Okay? And then light can come out that output port or that output port and be detected. Now, not one detector now, but two detectors. And what we have, these are again single photon counters. And I'm going to look for coincidence. That is to say, I'm going to look for situations where both detectors go click simultaneously within some window of my detectors. Okay? And now let us imagine that what is incident upon this beam splitter is in each port I have a single photon, which I'll just draw as a wave packet, which has one photon. So what can happen? Well, there are three possible things that can happen. I can have two clicks in D1. I can have two clicks in D2. Or I can have one click in D1 and one click in D2. Of course, photons could be absorbed, and maybe they don't go click, or maybe the detector goes click without a photon in it because it's got dark counts. But, you know, we got good detectors here, and well, we're just thinking in theory land, one of my favorite places to be. All right? So, we then have to ask ourselves, what are the possible histories that can lead to these outcomes? Right? Well, in this case, 2 clicks in D1, what can happen is the first photon gets reflected and the second photon is transmitted. Right? So this is reflection transmission. We can have the opposite happen, where this photon gets reflected and that photon gets transmitted. What about this guy?
Both reflected or both transmitted.
Right. There are 2 possible histories that can lead to the same final outcome. I could have a situation, as Jamie said, where both of them are reflected. That can lead to this case. And that would give me a click in my coincidence counter. Or I could have the situation where they're both transmitted, which would lead to this. And I have to superpose, this is my reflection amplitude or transition amplitude associated with that beam splitter, which I can calculate from classical optics, what the amplitude is for the electric field to be reflected in transmission is exactly the same coefficient that would appear here. And I just have to superpose them. And it turns out, because of unitarity, time reversal invariance, which we studied last semester, that this is 0. Which means there is destructive interference between these 2 histories. It's only the case if these 2 histories are indistinguishable. If they're distinguishable, well then we add the probabilities rather than adding the amplitudes. So if I were to say put in some kind of delay line in one of the arms of the interferometer of this kind of, right, and looked at it as a function of delay and looked at the coincidence counts, what I would see is right when the delay, I'll call that delta t, is 0, I see no coincidence because of the destructive interference between those 2 paths. But as I increase it, as the wave packets start to become distinguishable, I'll see, and then I'll get some ultimate. And this is what's known as the Hamel-Mendel dip. And the width of this dip is in some sense the size of the wave packet. And this is really what Hamel-Mendel, if you read their paper, and I was just a starting graduate student, then you would get it. They weren't really excited about this 2-photon here. They were really excited about it, about the idea that they could measure the duration of the wave packet by doing that. And that, in fact, these 2 photons were born from a process that we'll study a little bit later, parametric down conversion, effectively simultaneously. And so the duration of the sort of the time interval between the birth of these 2 photons was femtoseconds, even though it was done with CW light, meaning continuous wave for those of you who are not into literature. Meaning it's not a pulse, it's just a wave, but nonetheless the photons come out within femtosecond correlation. Okay, so one of the points here that where I'm trying to make in this discussion is the notion of interference that happens in quantum optics goes beyond the kind of interference that one sees of classical waves. There is no classical model of electromagnetic waves that can describe this phenomenon. I can describe a little bit. I mean, I can rig up some kind of correlated photons that are correlated classically, in which I see some kind of dip here. But the depth of that dip, the visibility of that dip, can never go to zero classically. And so that's one of the questions that we try to address, and it's one of the things that was part of a conversation for a long time in quantum optics of classical versus non-classical light. And this isn't actually a subtle question. It depends what the rules of the game are, as we will see. Whether something we want to call it classical or not depends on what resources we have available to us. So what we can say, if I'm doing a particular kind of experiment with a particular kind of detector, can I construct a theory within the constraints of classical physics that give rise to that experiment? But if I measure the system differently, I might have a different answer. So that is one of the subtle points that we'll get at. What we mean by classical versus non-classical light, to some degree, depends on what question we're asking. I would say there's a more modern way of addressing this question, which is classical versus non-classical in the question of an information processing resource. So what we've come to understand is that systems that are governed by the laws of quantum mechanics can be a resource for processing information and achieving certain information processing tasks like computation or communication in ways that are different from systems that are governed essentially by classical physics. I mean, of course, the world we believe is fundamentally quantum, so to say that is to say there's a subset of the quantum laws that we call the classical laws, right? And if it only is completely governed by that subset of the laws that we call the classical laws, then we call it classical, right? So, as we'll see, certain states of light are a resource for processing information in different ways. And that resource, again, depends on how we're going to use it. So whether or not something is classical or not depends on the rules of the game, what we're going to be allowed to use as our resources for processing information. I think that's a very interesting connection. And one of them that we see here, we went from, in the description here, the Dirac business of only single photon computer itself. This was a kind of single body physics problem. There may be many photons, but every photon is kind of independent from every other photon, and the events are just photon by photon. Versus thinking about the quantum electromagnetic field from a many-body perspective, where there are properties of that, in this case, two-body, not so many, but two is more than one, system that has a property that's different. And this property, as we'll see, is intimately related to the question of entanglement. A property of quantum correlation between more than one subsystem, in this case the subsystems are two photons, that opens the door to some non-classical properties that wouldn't exist otherwise. So that's going to be a big topic for us this semester. That's also intimately related, as we will see, to the problem of open quantum systems. Because what we mean by an open quantum system is a system where there are some degrees of freedom that we consider external to our system. And the quantum correlation between our system and those other degrees of freedom can lead to behavior that's different than if we have access to all those degrees of freedom all the time. All right, very good. So we just talked about interference as being an important hallmark of quantum mechanics, interference between indistinguishable histories and the assignment of wave functions to those histories. This is all kind of encapsulated by an important concept that we have in both classical and quantum optics, which is coherence. Okay? That's sort of, in some sense, the core subject of quantum optics. I would say quantum optics is really about the phenomenon of coherence in or by electromagnetic waves or electromagnetic fields. What I mean by that is that I could create quantum coherence in matter through light. And if it's quantum, I would call that quantum optics. So what is coherence? Coherence is, loosely speaking, the ability of a system to exhibit interference. So why don't we have coherence all the time? I mean, we said electromagnetic waves interfere. So what the heck am I talking about? In what sense is it to say that the waves don't interfere? Well, in classical optics, we would say that a system doesn't have perfect coherence if we have random electromagnetic waves. What does randomness mean here? Randomness, in this sense, we're talking about classical optics, is that there is some probability distribution. So this is what is called statistical optics. So the light that is emitted from natural light sources, or somewhat unnatural, like our fluorescent light bulb, we don't have a deterministic model for what the electric field is as a function of time. We can only sort of say statistically what we would expect. Why? Well, because we don't really have full information about the current that is generating that wave. That current is random because the ions in that neon light bulb, neon, whatever it is, fluorescent, I don't know what kind of stuff is in it anymore, it's undergoing random collisions with all the molecules and parts. So we have only a statistical description of that light. But it's a classical statistical description, which is to say that we describe it by a probability distribution, but not a probability amplitude, but a probability distribution. And we can understand that probability distribution as arising from incomplete information about what the source of the field is. Okay, so in classical statistics, for example, we might have, let's think about a quasi-monochromatic source. So I have something which has, and I might take the slide and put it through some narrow band filter. So it has some main frequency. It's not monochromatic, but it's quasi-monochromatic. So we would write the electric field then, in that case, as the real part of some amplitude that is slowly varying in time compared to some main frequency. That's a typical way to write this. So this is what we call the main frequency. And then this is some electric field which has a bandwidth, a range of frequencies that's narrow compared to omega. Okay? And we might write that in the following way. We might say, well, it has some polarization, it has some amplitude, and some phase. And all of these can be random in some way. So for example, when we talk about in classical optics, we talk about partial polarization. We talk about polarized light and unpolarized light, or partially polarized light. What we're talking about in that case is that the polarization is a random variable. So there is, of course, a whole theory of how you deal with partial polarization in classical optics. And it's probably extremely familiar to you. What you would do to do that is you'd write down a matrix. Well, typically we would say, if this is propagating in some well-defined direction, this thing, if it would have some amount of amplitude along two orthogonal vectors, say this is the main k direction. Okay? And all I really don't know, these are random variables, what alpha and beta are in some sense. So we would write this down as a matrix or a dyadic which would look like alpha squared E1 E1 plus beta squared E2 E2 plus alpha beta star E1 E2 plus alpha beta star E1 E2 E1. And then this is, yeah, that's right. Or as a matrix in that basis, okay. This matrix in optics is known as the Jones matrix. Anyone know optics in this way? ever study the Jones matrix calculus, take advanced optics? Anyway, you might call it corn, I call it maize. This is what we know in quantum mechanics as a density matrix. I'll come back to that just in a moment. Of course, this is really what I've written down here is not seen currently as a random variable. This is just there's some polarization that is wrote down as a matrix. To say that this is a random variable is to say I don't know what alpha and beta are, and really what I need to do is statistically average this over some probability distribution of possible alpha and betas. Okay? And so these are averaged over the whatever the model of possible statistical treating those alpha and beta as random variables, right? And then this is really that. And that's what's known as the Jones matrix, the Jones calculus of partial polarization. There's nothing to do with quantum mechanics per se. This is just about classical statistical optics. Now, so this is coherence from the point of view of classical optics. What about quantum coherence? In what sense do we say that a quantum system is not perfectly coherent? Well, what that means is, in this case, is that we have incomplete information about psi. All right? In the same way here, we had incomplete information about the electric field, which was the object that told us about how the field interfered. We could lose coherence if we don't have complete information about that. And that could be incomplete information on any of these variables. I just discussed the partial polarization, but it could be I have, I don't know the phase or the amplitude or any of them all combined. So, in the same way, we define a calculus or a formalism, as you know, for dealing with this. So now I'm going to talk, now I'm talking about state vectors rather than wave functions. And if I have incomplete information about that, one way of saying that is that I might have some probability distribution. So this is to say, I might have some collection, I have some possible set of wave functions that could describe, or state vectors, that could define my system, but I don't know which one it is. And it's described by some probability. This is what's known as an ensemble decomposition. And that ensemble decomposition can be expressed in a compact way, as we know, as we do, in terms of the density operator. So we would write the density operator, which is to say, a way of combining all of the possible states as an operator. And that's now our description of the state, where we don't know which wave function was prepared, or I should say it this way, what wave function we should assign to our system. But we know, for example, some probability. We have assigned some probability distribution to possible states that describes this. This is the density operator. Now, the density operator is going to be the star of our show this semester. It's very important that you really have density operator under your belt. We studied it last year If it's not something that you firmly have under your belt, we need to work on it. Okay? You guys have questions?
I'm sorry.
Please, no. You got folks, interrupt me anytime.
No, I mean, Paul, I was just, was expecting like off diagonal elements, I guess. But
Sure. Well, we're going to get into all that right now. Just a quick review. Let's remind ourselves about a few things. So, let's remind ourselves of some of the properties of the density operator. It's very important. So, the state of the system, so we have this, now we have the state is one and the same as a density operator. Okay? The purpose of the state is that the state allows us to predict the outcome of measurements, or at least assign probabilities. Predict means assign probabilities. We can't really say for sure what's going to happen in quantum mechanics, but we can assign a probability. Okay? So, the rule then, if we have for a given state, we have the Born rule. That way we just said was related to psi squared. So if I want to know what is the probability to find psi, or phi, given psi, well, that probability is equal to the square of the probability amplitude, right? If I have a statistical mixture, which is another way of saying what this ensemble decomposition, this is what we call a statistical mixture, as opposed to a coherent superposition. If we have a statistical mixture of different possible psis, so now I ask what's the probability to find, for example, phi given rho, which is one and the same with this particular ensemble decomposition. Well, what I have to do is average over, classically average, over all the possible states in my ensemble decomposition. This, of course, is equal to the complex conjugate times that, which is equal to that, which is equal to that. So the probability of finding that phi, given the state rho, is given by this matrix element, this diagonal matrix element. Or another way of saying it's the expectation value of rho with respect to this phi. This, of course, if this is a probability, is a positive, or I should say non-negative number. If this was supposed to be a probability, right? So the fact that this must be true no matter what phi is to say that the operator rho, whatever it is, must be a positive. That's one property of the density matrix. It has to be an operator that's positive. Which is one way of saying that is that its expectation value with respect to any vector is always non-negative. We say positive, we really should say non-negative, but we always say positive. Could be zero. Of course, we see from, and this also should be a real number, and that's clear that this operator, if this is a real number, because these are probabilities, that this operator is permission as well. Right, that is clear because this P is a positive number as well. We take its conjugate. That was positive. And if we want this to be normalized, then we want the sum of probabilities over all the possible distinguishable states to add to 1. That is to say then that the sum of the diagonal matrix elements adds to 1. So that's normalization. Now, as Zeke was suggesting, we can look at this in a matrix representation in the same way we just did for the Jones matrix, and think about diagonal versus off-diagonal elements. Right. So if I think about a particular state within my statistical mixture, and I expand it in a basis. So now let me just say that there's some E alpha, and I'm just for the moment think about this as a finite dimensional Hilbert space with some dimension D. So this is the basis of the Hilbert space. An individual state here can be expressed in terms of this basis for that particular state K, psi J, right? And the density operator then is the statistical mixture of the outer products of these guys. So I'm gonna be quick and dirty here and just move the sums around. See alpha J, beta, J star, alpha, beta. Just plugging that into our definition, right? This is just what is not quite erased over here. This is the statistical average of possible probability amplitudes associated with those basis vectors averaged over the statistical distribution of possible states in our statistical mixture. These are the matrix elements, rho, alpha, beta. Is that clear? It's important. So what we see here is that the information about the phase in superposition is contained in these off-diagonal elements, right? So if I look at a particular matrix element, rho alpha beta, let me write it out in more detail. Where I have written this just in polar decomposition of the complex amplitude. So a particular complex amplitude has an amplitude and phase, And what we see here is that the phase relationship here is contained in these off-diagonal matrix elements. And interference, whether it's constructive or destructive or somewhere in between, depends on the relative phase between these amplitudes. And the question is whether those relative phase matters or not depends on whether or not they're washed out. I mean, let's suppose that were the case that these amplitudes were the same, the magnitudes, but the phases vary from component to component. Then that could average out this phase, make it zero, close to zero, which would reduce the coherence. So, what we said here is that diagonal matrix elements, just to summarize this, what we have is that the diagonal elements, which are sometimes called the populations, that's a jargon we use, is related to the probability to find the particular basis vector, if we think about this as a matrix representation. The off-diagonal elements are known as the coherences. And they're called the coherences because those are the elements that dictate the potential to see, so let's just say rho alpha beta, potential to see interference between histories involving the two possible states, whether those two components interfere with one another or not in a particular experiment. Whether the probability of seeing a certain outcome depends on superposition between them is encoded in the off-diagonal element. All right, so, yeah, please.
Would you be able to see the strength there, like the strength of the interference through those off-diagonal elements?
Yes, indeed. So one way of looking at the strength of interference is, for example, in the visibility of interference fringes. So, you know, we might have in a, let's say, we have our favorite two-path interferometer, the Mach-Zehnder interferometer, which has two mirrors and two 50-50 beam splitters. And there are two paths that, say, lead to a particular, all right? And then I look at how much intensity falls, right? There are two paths here. I can decompose and think about these are my two basis vectors, E1 and E2 related. I'm being extremely loose about that, what that means, how a path can be a basis vector. But I'll be waving my hands right now. Okay? So there are two, I asked, are these two things coherent or not? Do they exhibit interference? And I say, look at this, I'm going to displace this by a certain amount, delta L. You see, now if these were perfectly coherent, and I looked at what came out of this detector as a function of delta L, I would see something that looked like this. Where if this was the intensity over here, all the intensity comes out here. Right? And then it goes down to zero. On the other hand, if I put in some rotating ground glass that puts random phases on here, which mixes up, decoheres, loses the coherence between these guys, so it puts some random phase and they do it in some way, then what I'll see is, depending on the degree of coherence, I'll see something that might look like this, where the fringes don't get all the way up. The contrast of the fringes is no longer perfect. Well, and at some point, if it's completely incoherent, what I'll see is something which is completely independent. I'll see no interference at all, and I'll only see half the intensity. Well, where did the rest of the intensity go? It went up the other port, of course. So nothing's being lost here. The only reason I see, say, 100% go out this port is because there's perfect destructive interference out that port when there's a perfectly balanced interferometer. If I unbalance it, then I can make it that all the light, shifted by pi, then all the light will go out here and none of it out there, and that's the dip. Right? So the degree of coherence here would be measured by the visibility of those fringes, which would say the max intensity minus the minimum intensity as a function of delta L divided by the sum of those. And that's proportional to that off-diagonal matrix element. Okay. Yeah?
So that random phase that you put on D1,
Yeah.
that's like basically adding a probability.
That's right. So it'd be like kicking around this phase by some random amount and then averaging over what that is, and that can wash that out. All right, well that actually, and maybe before I get to that, there's maybe one other thing that I wanted to remind you about the density operator. And that is, so we have a property that is Hermitian matrix. It's positive. So first of all, because it's Hermitian, I can diagonalize the matrix. And it will have a spectral decomposition with some eigenvalues and eigenvectors. Okay? In a d-dimensional Hilbert space. And I can always choose these to be orthonormal. Now, expressed this way, rho is a statistical mixture of its eigenvectors. So one of the messages here to remind you of is that the ensemble decomposition is not unique. There's a unique set of eigenvalues, and to be the non-degenerate, there's a unique set of eigenvectors, although if there's degeneracy, it can always rotate within those degenerate subspaces. But writing the density matrix the way that's been erased, that is to say, when I rewrote it as this, I didn't say anything about the orthonormality of those sides. I can pick anything I want and form a density matrix. But there were an infinite, uncountably infinite number of different ensemble decompositions, which lead to the same density matrix. That's an interesting fact. It's sort of the way in which quantum probabilities and classical probabilities kind of get mixed up. We could associate some of that to, when we see a certain randomness in outcomes, we could assign some of it to a certain amount of randomness in the way the states were prepared versus some amount of randomness in the collapse of the wave function, if you want to call it that. Okay, so with that said, and maybe there's a problem set that needs to remind us about that if we get to the last semester, even if we did, if you don't remember it anyway. Yeah.
So if you can always diagonalize, that means you can
Yeah.
always think of it as some sort of, you can always think of the density matrix as being formed by pure states, is that?
Well, this is, I don't know if you, so let's remind ourselves about pures, because I'm about to do that. We can, this is a statistical mixture of pure states. This is also a statistical mixture of pure states. What I'm saying is that there are different, you can mix pure states in different ways that yield the same mixed state. There's no unique decomposition in terms of the statistical mixture of pure states. Now, what's a pure state? A pure state is a state defined by a single psi. Which is another way of saying that is that the eigenvalues of rho are what?
0, 1.
That's it. One of them, this guy is one of these. It's a case where one of the lambdas is 1 for, say, alpha, lambda 1 is 1, and lambda 2 is 0, ... lambda sub d is 0. All the rest are 0. So the spectrum of the density matrix for a pure state has one eigenvalue that's non-zero, and it's normalized, so that eigenvalue is 1. Anything else we call a mixed state, which is to say a mixed state cannot be expressed this way. It must be thought of as a statistical mixture of at least two different pure states. It could be a statistical mixture of many, many different pure states, depending on the spectrum. And moreover, I should say, this number j can go up to arbitrary n. It doesn't have to be the dimension of the Hilbert space. I can mix together an Avogadro's number of spin 1/2 states. And that would be some mixed state. Of course, it would still be a 2x2 density matrix, right? A mixed state is something where the eigenvalues don't have that. And we can detect that. The Snell test for that is the following, is one measure of the mixedness. How mixed is the state? How incoherent is the state? Is by its purity. We can do a purity test on our many different ways. Everything, as you see, the degree of purity or mixedness just really is a function of the spectrum. We know the spectrum, we know how mixed or pure the state is, right? And one way of looking at that purity is by looking at the sum of the squares of the lambdas. That's called the purity. Okay. Now, if it was a pure state, that's the maximum value of purity. And what is that value? 1. Okay? What's the minimum value of purity? Is it 0? I mean, for an arbitrary dimension. Well, what state is the most mixed? What is the most mixed state?
When all probabilities are equal.
That's right. So in that case, if all the probability, that's to say all the lambdas are equal, and I have d different ones of them, and it's normalized, then what are all those lambdas?
1 over d.
1 over d, right? So that is the case where all the lambdas, so every lambda is 1 over d. So that is, to factor that out, and that, of course, is proportional to the identity matrix. Okay? By the way, this purity, the sum of the squares of the eigenvalues, can be written in a basis-independent way, not just dependent by looking at, because this is the trace of rho squared. Right? When you square a row, you get lambda squared in the diagonals. And then when you take the trace of that, you sum the lambda squareds. So the trace of rho squared is the purity. So trace of rho squared is 1 over d squared times the trace of the identity. The trace of the identity matrix is d. So this is 1 over d. So that's the minimum purity. All right, let me just conclude then. I'm sure I've forgotten other things I wanted to say, but about, just make one connection now to what we discussed about the notion of incoherence in classical statistical optics and incoherence in quantum coherence or quantum interference. So what we said is that we have quantum mixedness. Where does it come from? Well, what we said is this comes from incomplete information about psi. And there are two kinds of ways that we typically think about that. One is I can think about there is a preparer of psi who doesn't share her information with us. With the measurer, the person who measures the state. So for example, you know, I got at my disposal a CERN-Gerlach apparatus, and I can make a spin, let's say spin 1/2 particle along any direction I like, and I tell you, well, I got this fair die, it's got 6 sides to it. If it rolls 1, I'm going to send you spin up along X. If it rolls, etc. I can assign to every face of the die a probability of sending you a certain state. I send it to you. You don't know what I send to you. You have incomplete knowledge, but we do share what probability I'm going to send that to you. You would assign a state to your system consistent with that. Okay? So that's one way. And that's the kind of thing that, for example, is done in quantum key distribution. You send certain states, the preparer sends certain states, in this case Alice is sending to Bob, and doesn't only send some, share some probabilities, and afterwards they assign some key. But there's another way that might occur, which could be incomplete. So this is clear why there's incomplete information. The information is in Alice's head, but she didn't share it with you. Another way could be that the information well, let me say it this way. Complete information exists only about a global system, but not about its parts. So quantum mechanics is quite bizarre in a number of ways. This is one of the most bizarre. We can have a situation where we have a system made up of parts, say 2 parts that are drawn loosely as being tied together somehow, part A and part B, for which there exists a pure state that is complete information about the whole, but there is no way to assign to this a state to psi and a state to A and a state to B. There's just no consistent assignment that would be consistent with all the measurement outcomes that would happen on A and B. That's to say, some information about A is contained in B in some way. And if we were to then to try to assign a state to A alone, the only consistent assignment would be a density matrix, and same here. That is to say, the pieces are mixed, even though the whole is pure. And that is a completely quantum phenomenon. There is no, it's just inconsistent with logic. You cannot have complete knowledge of the whole, but not knowledge of the pieces. But in quantum mechanics, that's the way it goes sometimes. And this kind of quantum correlation, at least this is, of course, entanglement. And it's something that will typically happen in a system where we might say this is our quantum system that we care about, and this might be the environment in which the system sits. And because these two can become entangled, what that will mean is that we lose information about our system to the environment. And whereas a system might have started out completely pure, over time it becomes mixed. It loses coherence. And that process is what we call decoherence. So we will be studying that in some amount of detail this semester. It is something that is unavoidable. It will happen. We work really hard to avoid it, but it's impossible. Although maybe we can reverse it. We have quantum error correction that would be nice. That's a whole other story. And then we'll pick that up next week. All right? Very good. All right. So again, we don't have lecture on Thursday. I will be posting notes and videos are becoming. I'll be emailing you to let you know that they're there, or you can find them. And again, if there's concerns that you have about some of the background and not having seen this, come and talk to me, and